This problem asks you to consider how the surface temperature of the Earth changes as you halve and double its radial distance from the Sun. So the setup of the problem looks like this. Here you have the Sun, and you have a radial distance d at which Earth currently exists. And we'll call this d. When you have this radial distance, the Earth would be much closer to the Sun, and this would be at 1/2 d, 1/2 the current orbital radius of the Earth. And if you, of course, were to double this radial distance, Earth would be here, and this would be 2 times d, or 2 times the current orbital radius of the Earth. So this problem gives you a couple different proportionalities to work with. It gives you that temperature, the surface temperature, is proportional to power given off by the Sun to the 1/4 power. And it also gives you that the solar flux is proportional to the inverse radial distance of the Earth. So the trick is to relate these proportionalities and to come up with a usable equation. So we begin with flux first. Flux is equal to, power is equal to the flux times the surface area, which you calculated earlier in the series of problems. And if we were to look at the units, flux is given in terms of watts per meter squared, and area is meter squared. So we cancel these out, and we get back units of watts, which is the unit of power. So because power equals flux times area, we can also say that power is proportional to, using this proportionality, the surface area divided by the distance squared. And that's just a proportionality from multiplying these two things together, where we assume that flux is proportional to 1 over the radial distance. Great. So now that we have this proportionality, we could plug the proportionality for power back into the proportionality for temperature. And we can say that temperature is proportional to the surface area divided by the radial distance squared to the 1/4 power. So now we have a relationship between temperature, radial distance, and surface area. And as we'll see, this A actually drops out of the equation, and you don't need to consider it. But we will keep it for the sake of this example until the very end. So how do you get an equation that you could compute with out of these proportionalities? Well, you're actually given the fact that the temperature of the Earth at its current orbital radius is 300 degrees Kelvin. So we'll call this T0. So T0 equals 300 degrees Kelvin. Moreover, that this proportionality applies to the Earth at its current radial distance. So let's work with, for example, 2 times d. How do we get an equation that we can use to compute the surface temperature of the Earth at twice the radial distance that it currently exists at? Well, we can actually set up a proportionality to do that. And we can make the assumption that, the temperature at 2 times the radial distance over the temperature at its current radial distance equals, and let's substitute in the proportionalities. Let's say that these changes scale equivalently. So we can say that A over, let's call this d2x, which we can just call that, let's call this 2d. 2d to the 1/4 over A over d, sorry, these are both squared, to the 1/4. All right, so we have this relationship. So we can see that because we have a way to isolate the surface temperature of the Earth at 2D from this equation, we can actually solve for the surface temperature of the Earth at twice the radial distance. Okay, so how do we go about doing this? Well, let's first simplify this problem. We can also say that this is equivalent to a to the 1/4, well, just applying our power law here, over 2d to the 1/2 over a to the 1/4 divided by d to the 1/2. We've just brought our powers and brought them into the respective fraction. So we can just invert the denominator and say that this also is equal to a to the 1/4 over 2d to the 1/2 times d to the 1/2 over a to the 1/4. And we immediately see that the a's drop out of the equation. This was not necessary to begin with. We could have just said that temperature was proportional to 1 over distance squared. All right, but there's still more work to do. I'm just going to come back over here and say, let's see, we're just coming back over here, and we can say that d to the 1/2, and we can distribute our 1/2 power. We could say 2 to the 1/2 d to the 1/2. All right, oops, that's a subscript, not a superscript. There we go, 1/2. The d's cancel, and we're left with 1 over square root of 2, or 1 to the 2 to the 1/2 power, right? Okay, so this ratio is constant. This scales linearly. So how do we get t2x back from this relationship? We just found that t to the 2x over t naught equals a constant 1 over root 2. Multiplying both sides by t naught, we can say that t to the 2x equals, let's see, t naught divided by root 2. That is how the surface temperature of the Earth changes with respect to radial distance. I'll leave it to you to plug in the numbers and compute this value, as well as set up the similar equation for 1/2 d and plug in and solve the value. So that's it for this problem, and I will see you next time.